Unit 4 Chemistry, Chapter 12, Part 2. Now we're looking at a second technique called nuclear magnetic resonance. And there's a few different types of these, so it's going to go over a couple of videos. This first one, we're looking at how we can use it for identifying carbons in an organic molecule. So NMR is really useful. Again, we're using part of the electromagnetic spectrum. And again, we're absorbing energy, which is moving something to a higher energy level. Okay. In this case, we've got really low energy. So it's not going to move the electrons, it's not going to change the bonds. What it is going to do is change the spin of the particles in the nucleus. Okay? Bet you didn't know they spun. They do. Okay? As well as having charge and mass, if you've got an odd number of nucleons, then they also have an overall spin. Okay? So a nucleon is something in the nucleus, a proton or a neutron. If I've got two of them, one will spin in one way, the other one will spin in the absolute opposite orientation, so they cancel each other out. And that's what happens anytime you've got two or any even number of nucleons. But if I've got an odd number, they can't cancel each other out. So there will be an overall spin. Okay? Now, just hanging around as they are, that's absolutely fine and normal, and the two orientations are just equal to each other. But if you put them in a magnetic field, then they're either going to line up with the magnetic field or against it. Okay, so absence of magnetic fields are all over the place. In the magnetic field, they're either going to line up with it or against it. And what we can use NMR to do, that very low energy wavelength, is we can use it to switch their spin. So we could take some of them which are lined up with it, okay, and we can then switch them so they line the opposite direction. Okay, so aligning with the field is lower energy, aligning against is higher energy. And just like with IR, when a certain wavelength corresponded to a certain bond, okay, same idea. The certain wavelength now is going to correspond to a certain type of environment. So our first type of NMR is carbon NMR. Now carbon 12, no overall spin. But carbon 13 occurs naturally, it's quite rare, but it occurs naturally and it's got spin. And it will be incorporated naturally into samples of molecules. So what we can use it to do is identify what environment that carbon is in the molecule. Okay? And when we talk about environment, what we mean is basically what's that carbon bonded to, and how many different types of things are there bonded to different carbons in that environment. Okay? So we might have a carbon which is bonded to 3 hydrogens and something else on the left. Okay? That's got a relatively low, what's called chemical shift. Don't worry about how it's measured in ppm, it just is. Okay? Or it might be in a CH2, or it might just be CH, or as we go up we might see it starts to get bonded to some very electronegative elements. Yeah? So we might see it's bonded to some oxygens or a C double bond O. Okay? And that's going to increase the chemical shift. Okay? So what we would see is a line, okay, along the bottom. That line along the bottom means no absorbance. And then we'll see these peaks. Okay? Normally for carbon NMR we see them as straight lines. Each peak tells us we've got a carbon environment. So the first thing I'm going to look at is say I've got 2 peaks. That means 2 different carbon environments. And that's the single most useful bit of information you're going to get from a carbon NMR. Okay? Or any NMR, to be honest. You might say, hang on, there's 3, what's this TMS? We'll come to TMS in a bit, but that's basically our reference value. That's what sets where 0 is. Everything else is how much did it absorb compared to the TMS. Okay? The other thing we can see, though, is that these 2 peaks are basically the same height. That means that we've got basically the same number of carbons in each of those environments. In this case, it's 1. It could be that we had 2 in each of those environments. That would give us the same type of spectrum. Okay? The other thing worth noting, the CH2 is further to the left. It's bonded to the OH group, which is going to increase its chemical shift. Okay? So this is TMS. Okay? TMS is tetramethyl silicate. It's a silicon bonded to 4 methyls, so tetramethyl. Okay? We use it because these bonds don't occur naturally. Okay? And we also use it because there's lots of carbon-hydrogen bonds, there's 4 carbons in it, so it's going to give us a nice strong signal. Okay? And therefore, it's not going to interfere with it, it's just going to mean it doesn't matter what else is there, we're going to get a nice strong signal that sets our 0 value, and everything else can be compared to that. If you are interpreting a carbon NMR, there are 3 things that you're going to look at in this order. Number 1, how many carbon environments are there? That's the number of peaks excluding your TMS. Number 2, what is the relative area or relative height of these? How do they compare to each other? Because that tells us the ratio of carbons in each environment. So this is a 1-to-1 ratio. Okay? That just means there's the same number in each. It doesn't mean there's actually 1 carbon. Yeah, it could be 1-to-1 is the same as 2-to-2 is the same as 3-to-3. We just know they're in the same environment. And the third thing and final thing, and to be honest, you're almost never going to look at it, is where on this scale are they? Because you can then look them up in your data book to try and identify what they are. But be very, very careful doing that, because finding a chemical shift of a certain value does not, repeat, does not specifically identify a certain type of carbon grouping. Okay? It simply may give us some other indications, but we would use IR to find what type of functional groups we've got. Okay? So this would be combined with other information. As I say, most of the time you will not use the chemical shift. If you're using it first, you are almost certain to go wrong.